Hi guys, this week we're going to be looking at Investigation 8, Streams and Runoff. As always, my name is Tessa. That's my email address. I'm not going to be hosting office hours this week because I'm at a conference, but feel free to email me to schedule an appointment. This is a cool lab with a lot of demonstrations, so I'm going to go over the PowerPoint slides with you, and then I'm going to demonstrate how to do the following questions in the assignment. Please hold on to your assignment at the end and turn it in whenever you go to lab for Investigation 9. There's quite a few announcements before we can begin. Remember that you either need to go on the field trip or do a lab paper to receive 30 points. If you did not sign up for the field trip, that means you have to turn in a 4-page lab paper by 5 p.m. on Friday, April 19th. So don't forget that. I sent an email with more detailed instructions, but please check out the lab manual's instructions there in the Roman numeral pages. Remember to cite in text where needed and to add a bibliography at the end. If you don't do that, it could potentially be plagiarism. If you have any questions about that, just email me. If you did sign up for the field trips, you're either going to go on Tuesday, April 9th or Wednesday, April 10th, depending on what ticket you got. We'll be leaving from the parallel parking spots just south of the building in between the fraternity house and Murray around 7:30 a.m. So please be there before 7:30. They're pretty strict about leaving on time. Be sure to check out the weather too, so that you can dress accordingly. We'll be on for just under 12 hours, so you want to be comfortable for the whole day. Bring your ticket with you as well when you show up to get on the bus. You'll also need a pen or pencil to write with, and food and drinks. I think it tells you also to bring a camera, but they're kind of just being cute with that. You don't have to bring a camera, and most people have one on their phone anyway. The field trip worksheet you'll be given at the beginning. You want to start working on that as we're traveling. It's not difficult to do, but you'll just be filling out little questions as we're traveling and at each stop that we make. You don't want to get behind on it. Again, it's not too difficult though. And that's how you'll get the 30 points. It's also how we know that you were there. Also, in case you haven't seen the schedule, we're not going to be meeting for lab during the week of the field trips. If you're in my labs, you'll know why. It's because most of my labs, actually all of my labs, are Tuesday or Wednesday, so it wouldn't make sense. So if I don't see you on the field trip, I'll see you for Investigation 9. The last bullet point that I want to talk about is Lab Exam 2. It's coming up very soon. It doesn't seem like it for you, but I promise it is. So Thursday, May 2nd is Lab Exam 2. It's going to be the same time of day as the first one, 5:30 to 6:30 p.m., and it's probably going to be in the same location, but it's not on the website yet, so I'm not quite sure. But if you remember, that was Engineering South 317. I'm also still waiting for the second released exam to be posted online. There's a link, but the link's not working. So once that is posted, just be sure to check that out. I'm going to use it in class a few times, but it's very helpful. I think it's probably the most helpful. Also, this is kind of new, but there's going to be an optional help session on Tuesday, April 30th. Last semester, Dr. Stadler did this before both exams, and this semester we had like a week where the TAs would do optional help sessions. So this is going to be kind of different. Dr. Stadler will be doing the optional help session on that Tuesday. It's going to be from 5:30 to 6:30 p.m. in Murray 035, but that'll be posted more closer to the date. I highly recommend just going to at least one help session, or at least looking at the released exam. Let's look at a little bit of review before we start the lecture for Lab 8. Last week we talked about soils and how soils are important for construction. The idea I want you to remember is that some soils are better than others for building. For example, we saw in the lab that only 2 of our soil series that were on our property were suitable for building a house with a basement. We knew this because of the verbal rating that was listed in the tables. It listed the soil series as not limited. So if that was a numeric rating, that would have been close to 0. A verbal rating of very limited, on the other hand, or a numeric rating close to 1, is a soil that you would not want to build on. If we had built our house on a soil, our house with a basement, on a soil series that was very limited, we would likely have to do expensive repairs. We also talked about how soils are categorized around the world. A more general categorization of soils are called soil orders. If you remember, there's 12 soil orders in the world, and 7 of those are in Oklahoma. On the flip side, there's over 2,500 soil series in Oklahoma. So those are the more specific categories. So make sure you know the difference between a soil order and a soil series. You don't want to get those confused. Very similar to the difference between a biome and an ecoregion. One's more general, one's more specific. Lastly, be sure that you know how to use a soil triangle. If you're given a soil sample, you can use sieve analysis or hydrometer analysis. Those are those two vocab words, the methods that we use. So you can use either of those to find the percent of sand, silt, and clay in the soil. And once you find the percent, you can use the soil triangle, the soil texture triangle, to find the soil texture. If you have questions about using that, please let me know. It's actually pretty easy. Let's go ahead and jump into the Investigation 8 lecture. You can follow along in your lab manual. Some of my slides are going to be a little different order than the sections of the investigation. In this week's lab, we're going to be looking at demonstrations of the stream table so that we can learn more about stream dynamics. We use a stream table in order to see how isolated factors affect streams, kind of at a small scale. We will see how nick points and deltas are affected by streams. Those are two of the vocab words in the lab manual this lab. A nick point is like a waterfall, which you can see on the left there. Notice in the picture that over time, as water passes over a nick point, the water erodes away the less resistant rock behind the waterfall. So this will eventually erode away. And as it erodes away, eventually that leads to the collapse of the nick point. So this will fall. Over time, as the nick point continues to collapse, it will move upstream. So it'll continue to erode, collapse, and then move upstream. In the first lab assignment question, we're going to demonstrate this phenomenon. So we'll also see a delta forming at the base of the stream table. When we say delta, we mean this right there in the shape of a delta. This occurs because as the stream slows down near the drain, near the base of the stream table, it slows down and it can't carry the soil that it had with it, so it deposits that soil. And as the stream deposits more and more soil, the path to the drain actually isn't the least resistant. So it starts moving out. It starts widening out. And eventually it forms a triangle like that. Next, I'd like to talk about how we can determine the direction of a stream when using topographic maps. This first bullet point might be intuitive for you. It might not, but I think it's actually kind of simple. We can use the height of contour lines on the map. So if you see the top right, that's really the map that I'm looking at here. So if you see that, you can actually see the elevations listed on the map. We know that water has to flow from higher elevations to lower elevations due to gravity. So we can just look for those elevations to determine which direction is downstream. Looks like there's Horseshoe Peak, something like that, at the top with 7,138. So 7,138 feet, perhaps. And I see 7,000 and 6,600. So the water would flow that way if there was a creek coming off of the peak. And I can also see 6,400 down here. So the water would flow that way. Second, we can use crenulation V's. You might remember this vocab word from the second lab. As we were drawing contour lines on topographic maps, we would draw a V, the shape of a V, as the contour line crossed a stream or a river. And that crenulation V always pointed upstream. And you can see that phenomenon on the second map. Here, the contour lines are like this 1,000 foot or meter contour line, and the streams are the dotted lines. So these guys, right? I'm trying to do their dots, but it's actually kind of hard. So those are the streams. And we can see that as the 1,000 foot contour line crosses the stream, it does so by pointing up. So that's the part right there. It points up. The crenulation V is pointing upstream. So I know that the direction of the stream's flow is this way. And the third way that we can determine the direction of a stream flow Again, this one might be intuitive for you as well. We can see where the tributary streams join the larger streams. So I think tributary is another vocab word, but I'm not sure. Tributary streams are these little guys. So all of the ones that are labeled 1. So that, kind of the lighter shaded ones as well. So all of those continued all the way around. Those are tributary streams. And you can see that as they connect to the larger streams, they kind of form a little Y shape, right? So for example, these two kind of form like a Y shape. And the tail of the Y points in the direction of downstream. Even these guys kind of form a Y as well. And the tail of the Y would point downstream. Next, we will discuss stream gradients and the tool that we use to measure gradients on topographic maps. Keep in mind, Dr. Stadler loves to ask questions on his exams about the tools that we use to measure things. A map measurer is actually an analog version of the tool that we'll be using in this lab to measure the length of a stream. So this picture down here, this actually shows not a map measure, it shows a digital map measurer, which is called a planimeter, right there. So this planimeter, you can see on the left side right there, there's a little wheel. So if I drew that, which is not going to be pretty, if I drew that, there's a little wheel that's at the end of the planimeter. There's also a wheel at the end of a analog map measure as well. So what happens whenever we're using these, we're trying to measure the length of the stream. So let me give you an example of why we'd need to use this. Instead of just measuring with a ruler, let's say our stream looks kind of like this. If we just measured with a ruler, that's how far we'd say the water traveled. That would miss a whole lot of the traveling. So the water is actually traveling quite a bit further, because right here you can see it doubles back, and actually all of the curves it's traveling further than a straight line distance. So that's why we actually use a map measurer or a planimeter. It gives us the actual length that the stream is flowing. So that wheel, what you're going to do with the wheel is actually trace along the stream. And as you're tracing, the planimeter counts how many rotations of the little wheel that you've traveled. And if you put in the representative fraction of your map, which you can see here, it says 1 to 24. That means 1 to 24,000. So they've input their representative fraction. So if you do that, then it will actually tell you how far your distance is relative to the representative fraction. And you can barely see that, but right there it says miles. So they've also chosen to make it calculate the distance in miles. So this is a really easy tool. All that you do is just follow along the stream, and it will tell you how many miles in the real world that the stream has traveled. So now that we've seen how we can measure distance that a stream has traveled, we can discuss stream gradients and how we calculate them. The gradient of a stream is also known as the steepness or slope of a stream. I know we don't use the term gradient that much, but some people use this in everyday speech. So the gradient of a stream, or the steepness of a stream, affects a lot of things, particularly the type of material that the stream is capable of transporting. So imagine a mountain. If we had a stream coming off of the mountain, let's say from snow that's getting melted, then you can see that the stream coming off of that mountain is actually pretty steep. So if there's rocks in its way, the stream might carry the rocks with it because it's going fast. That's going to be different than if you imagine a stream in the plains. If you imagine a stream in the plains, it's not going to be able to carry rocks along with it. The water's not moving fast enough. So the stream competence is the size of the particles that the stream can transport. This stream that we were just talking about with the mountain, it has a higher or a greater stream competence than a stream that would be flowing through the plains. We can find the stream gradient using this equation. This equation will probably be given to you on the equation sheet on the second exam. However, I don't like just using the equation given because G, V, and H don't necessarily explain what they mean. So please make sure you know what those stand for. G is the stream's gradient. That makes sense, but V and H don't make sense quite as much. So let's talk about what those are. G is the gradient. Usually it's measured in feet per mile. V is the vertical drop in altitude. You can find the vertical drop in altitude. Again, think about that mountain stream. You can find the vertical drop in altitude by looking at the difference in elevation of 2 points along the stream. Especially on a topographic map, if you can't find that, just use contour lines. And H is the horizontal distance of the stream. And that's what we're finding with the map measurer or planimeter and tracing along the length of the stream. That's telling you your horizontal distance. Whenever we input all of those in the equation, we can find the stream gradient in feet per mile because feet was our altitude unit and miles was our horizontal distance unit from the planimeter. Runoff is an important concept to understand, especially because it can affect our water, soil, vegetation, and infrastructure. Runoff is literally the water that doesn't soak in but runs off of a surface. It's affected by a few things. One of those factors is the permeability of a surface, or how quickly water can soak into the surface. Think about the difference between how quickly rain can soak into the asphalt versus how quickly rain can soak into grass. Another factor that affects runoff is the slope of the land surface. This is because rain that falls on the steep slope of a mountain may not have time to soak into the ground before it runs off. Lastly, the intensity of precipitation also affects runoff for similar reasons. Think about how much runoff a heavy rainstorm produces versus a light rain shower. We can calculate runoff by using this equation, where runoff is measured in acre feet. Whenever you see or hear that unit, think of an acre of property being covered in 1 foot of rain. So this foot is not going to be to scale, but that original rectangle I drew was an acre, and I went up 1 foot. So you've got 1 foot of water standing on an acre. That would be 1 acre foot of water. The way to calculate runoff is by multiplying the acreage in acres times the runoff coefficient, which is table 8.1 on page 8-4, times the rainfall in feet. Because the runoff coefficient doesn't have any units, you're just multiplying acres by feet, so your final runoff calculation has the acre feet unit. Let's look at the runoff coefficients in that table. You'll notice that the asphalt or concrete land use type has a runoff coefficient of 1. So that means 100% of the rainfall on asphalt or concrete will run off. Compare that to downtown and business, which has a runoff coefficient of 0.8. That means 80% of the rain will run off of downtown and business land use. That's probably lower because downtown and businesses usually have some grassy areas or like trees planted somewhere. Furthermore, I want you to look at the difference between single family homes and multifamily homes. If you're not sure what those two things are, think of multifamily homes like apartment complexes, and think of single family homes like just regular houses that one family would live in, right? A multifamily house probably has a larger parking lot. They also probably don't have as much land per family. So that's probably why they have a slightly higher runoff coefficient. Lastly, let's look at how runoff collects into our streams. Water runs from higher land to valleys. Interfluves are the hills or higher land that separates the valleys. You can see that in our picture to the right. And a collection of valleys that are within the highest interfluve, which is the drainage divide. That collection here, so all of these valleys are a drainage basin. And it's the drainage basin that empties into our streams and rivers and waterways. So pollution can be carried with runoff and have a huge impact on our water. Let's go ahead and start working on the questions. Again, please keep your assignment for Lab 8 with you so that you can turn it in when you go to lab for Lab 9. The first question is about our stream table demonstration. For part A, we will be looking at the stream table as the water flows from the top of the stream table down to the drain. Part A wants you to find the velocity of the water. We'll do this by timing how long it takes for the water to go from the top to the bottom of the stream table. For both trial 1 and 2, please write that the migration distance is 203 centimeters. That is the length of the table, the length of the stream table. Now let's watch to see how long the water took to travel the length of the stream table, and write that down in your seconds for trial 1 and trial 2. So this is the stream table. You've actually walked by it many times, and that's Shelby's dog Panda, which you'll see again later in the video. So what we're doing is turning it on. There's a pump at the end under the drain, and whenever I turn on the pump, it pumps the water back up to the top, and now you can see that it started. So for trial 1, we're timing it, and I'll let you know what the times were, but you could also look at the time on your video. And you'll notice that trial 1 takes actually quite a bit longer than trial 2, and that's because the water is soaking into the soil. You'll also notice that right now what's happening is that the stream is meandering. It's trying to find the path of least resistance, and it's not the path that we carved out, which was surprising to us. Also at the end, you don't have to notice this just yet, but there's a nick point that's going to start forming. It'll look like a waterfall pretty soon. So right here, we already ended, it had already reached the drain, and we're showing you kind of a delta formation. And here we can see the time. So the first trial's time was 45 seconds. We started the second trial, and you can see that really quickly the water reaches the drain. So that was 13 seconds. So now that we have that information, let's go ahead and write it down so that we can solve for the velocity. So we saw that for trial 1, the time was 45 seconds. Just like I said before, you should still have a distance of 203 centimeters listed here. And we saw for trial 2 that the time was 13 seconds with a distance of 203 centimeters. So I want to point out, whenever you're solving for velocity, go ahead and look at the units, and you'll be able to easily put together an equation. And I'll do an example. Let's say I walked 2 meters in 10 seconds, which is kind of slow. So my velocity would be 2 meters divided by 10 seconds. And that's because I want my velocity in meters per second. So I would have 1/5 or 0.2 meters per second. Similarly, you're going to be setting up your velocity just like this, where you're dividing the distance in centimeters this time by the seconds for each of your trials. So go ahead and work that out. And then we'll go ahead and look at part B. So let's look at what we did for question 1B. You can see that the water is coming down here. The nick point is going to be the edge right there. So you can see it's kind of starting to form like a waterfall. And what we're seeing here with the ruler beside it is that the nick point is traveling upstream. So it's collapsing in on itself. And we've probably stopped by now, because I was trying to stop it when it got to 6 inches, which is what I'm showing you there. That was about 20 seconds. And now we're at trial 2. Same thing, and I've got the ruler set up right beside it. So we're seeing again the nick point is moving upstream. And this one actually is really easy to see. You can see along the edges how it's moving. So we stopped it when it had approximately moved 7 inches. And I don't think Shelby shows you in this video, but I'll tell you the time that took was 23 seconds. So go ahead and write down 23 seconds and 7 inches for trial 2. So let's go ahead and start setting up the problem for 1B. This is where we're measuring the migration rate of the top of the nick point from the start to the end of the 2 trials. So I want you to go ahead and write down the time in seconds. You probably saw that the first trial took 20 seconds, and the second trial took 23 seconds. Now the migration distance, that's kind of a little trickier. So we were using a ruler that only had inches on that side. So I'm just going to write down the conversions down here because that's not what we asked you to do. So the migration distance for trial 1, the migration distance was 6 inches, which is approximately equal to 15 centimeters. For trial 2, it was actually 7 inches because we stopped it a little bit too late. I was trying to get exactly 6. And 7 inches is approximately 18 centimeters. So for trial 2, go ahead and write down 18. You'll see that the migration rate is what you're solving for. And this is again in centimeters per second. And again, if you use the units to your advantage, all that you have to do is divide the migration distance by the time. Centimeters over seconds. For part C of question 1, we're looking at what happens to the stream as a brick is placed in the way. The brick is analogous to more resistant bedrock or just an obstacle. So look at what's happening to the stream as it encounters that brick. We also wanted to throw in a little bit of delta formation in there. But yeah, look at what's happening as the stream encounters the brick and just describe what's happening there. So now that we've seen what the video shows as the brick is placed in the stream, go ahead and answer for number C. Just write down what happens to the stream as it encounters the brick. And you don't have to write a lot for this, but once you're done, go ahead and move on to 2. For part A and B, we're going to see some video first to identify where Brush Creek is on the map and figure out the direction of flow. We can see we're at Stillwater South Quadrangle. Now let's find Brush Creek. Panda found it right there. So we can see that says Brush Creek. We can also see there's some tributary streams flowing into Brush Creek right there that say West and East Brush Creek. And I'm also going to highlight that some of the elevations at the top say like 889. And if we go further down Brush Creek, we start seeing some lower elevations like 848. So let's go back to the question. 2A says to find Brush Creek, which we did, and it says what's the general direction of flow of Brush Creek? So we can use a few of the things that we saw there to determine this. If you remember my slide, the first way that we can tell the general direction of flow would be to look for the elevations. This is not what you need to write here, but you need to actually write which direction it is. I'm just giving you some hints. So you can use the elevations in that video that we saw. The second way that we could figure out the general direction of flow would be to look for those crenulation V's. However, I didn't really get a great video that showed those. So let's look at the third possible way to figure out the general direction of flow. That would be to look for where tributary streams form a Y. If you remember, the tributary streams form a Y that points downstream. And by tributaries, we mean West Brush Creek and East Brush Creek. So those are two tributaries that flow into Brush Creek. And you can see on the image at the right how those streams flow together. For question 2b, let's just look at the scanned photo I took of the Stillwater South Quadrangle. You can see that I've got section 17, 18, 19, and 20 here. And in section 17, that's where West Brush Creek and East Brush Creek are. And so we can see that West Brush Creek kind of continues up right there, and East Brush Creek looks like it is right around there. I'm going to look for the highest contour elevation that we can find on either East Brush Creek or West Brush Creek. This index contour, which is the darker contour line right there, I just traced over it so poorly. It says 900 feet. So remember that as we go out from the 900-foot contour line, we're going to be decreasing in height by 10 feet. So this next contour line, which starts right here, would be 890, and this next one would be 880. So what I would like you to do is tell me, what does that make this part of West Brush Creek? So for part B, go ahead and write the highest height contour that you think was on West Brush Creek right there. That was 900, that's 890, 880. What does that make West Brush Creek? And part C, we can go ahead and do as well. In part C, we're just going to use that picture to the right. We can see that East and West Brush Creek join to form Brush Creek. So what we want you to do in figure 8.1 here is literally to sketch the paths of the creeks with solid lines. And we have the sections labeled 17, 18, 19, and 20 to help with that. So I will scroll back over. So that's the first part. And I'm going to go ahead and do that. I'll erase all this stuff. So I see section 18 and 17 here, and 19 and 20 are below. So that's kind of where we're at. What I would do is sketch over just slightly like this. Alright, something like this. It doesn't have to be perfect. And I might want to like put a little extra things. So I wanted you to just highlight where the creeks are. The second part of the question says, with dashed lines, draw the drainage basins of the 3 creeks in the 4 sections shown in figure 8.1. So if you remember, I mentioned that drainage basins were the collection of valleys on one side of the highest interfluve. So let's go back over here. What I want to do is draw the interfluves. They're the easiest things to draw. So what you'll be doing to draw the interfluves is you'll be following these like bumps in the contour line. So you see right here and here and here, there's kind of bumps all pointing this way. So some people call those the toes. So you'll be following the toes, like what's on your feet. You can see that the toe kind of points towards where one of the Y's is. It doesn't always do this, but in this case it did, and a lot of cases it does. So another interfluve would be right here, and so forth. So I just want you to continue to trace over these interfluves, and that's what I want you to do for this question. None of the drainage basins are actually fully on this picture, which is fine. So just draw with the dashed line the interfluves. After that, we can move on to 3A. It's asking you to find Cache Creek as it flows southward through sections 18 and 19 to the south edge of the map. And then to use a map measurer, we're going to use a planimeter to calculate the gradient of this part of Cache Creek. So I just wanted to point out Cache Creek is in sections 18 and 19, which we have right here. So what we're going to do for this is calculate the gradient. We're going to use that equation G equals V over H, where V is equal to the vertical elevation drop, and H is equal to the horizontal distance. If you look at the units, you see that the answer should be in feet per mile, so our vertical elevation drop will be in feet, and our horizontal distance will be in miles. I also want to point out the horizontal distance, that's what we're going to use the planimeter for. And the vertical elevation drop, that's what we will use the contour lines for. So Cache Creek is actually this guy right here. Looks like he kind of does like that maybe, and like that. So let's see what the video shows us. We can see in the video that we're looking at section 18. If we look up to the top of the creek in section 18, we're at 1,300 feet in elevation. And if we look at the bottom of section 19, the lowest elevation is 1,250 feet. So what we're planning on doing is finding the gradient from the top of the stream at the top of section 18 all the way down to the bottom of the stream in section 19, right there. And to do that, we needed to find the elevation of the top and of the bottom, and that'll give us our vertical elevation drop, and then we'll go over it with a planimeter to see what that horizontal distance is. The video really helped because we got to see what the index contour was. It says 1,300 feet. So that's going to help us find the elevation of the top of our stream. You can see that the index contour is that darker one right there, and there's a lighter contour line just to the right of it. Right around there. And we have another lighter contour line right there. So if that's 1,300 feet, the index contour right there, the next contour is 10 feet down. That should be 1,290. And this next guy should be 1,280. So that's actually what I'd say the elevation is of the top of the creek. So we're going to use that, and we need to also figure out what the bottom of the creek's elevation is right there. So first let me write down 1,280 feet. And we're going to subtract from that whatever we find is our elevation at this point down here. The video showed that this index contour is 1,250. So we can look to see how many contour lines the stream is away from that. If that's 1,250 right here, then that contour line would be 1,240. And that one would be 1,230. So I'm going to assume that 1,230 feet is the elevation at the bottom of the stream. So that would mean that our vertical drop V is equal to 50 feet. So that's what we're plugging in for V. V is equal to 50 feet. And H, we're going to find in the next video clip. So here's the video of us using the planimeter to find the horizontal distance across the creek. So you can see I'm actually tracing over this really delicately because I want to make sure I get every curve of the creek so it's not the straight line distance. And it looks like our results were 2.255 miles. So just to wrap up 3A, the horizontal distance H will be 2.255 miles. 2.255 miles. So you'll want to plug that in and solve for it. And please put the units in your answer. Let's move on to part B. So we're going to have the same setup here. We're going to have a gradient that we're solving for using the vertical drop V and the horizontal distance H. And I'll go ahead and show you where our video will be looking at. So here you can see Brush Canyon right there. The stream, I believe, starts right here and kind of does like that. So I'll be looking for the elevation right there. It's actually given to me, and I'll be finding the elevation there using index contours and working my way down just like the last question. And the last thing I'll do is trace over it with a planimeter. So let's go ahead and look at the video to see what we got for the vertical drop and for the horizontal distance. So here I am looking for the elevations. So this video shows me the top elevation where we're starting, and it shows me a index contour where we end. So my vertical drop we can find by using the first number that we just saw, which was given to us as 1,457 feet, and subtracting from that our elevation at the end. So the thing that's kind of tricky about this is that my picture is not very clear. But I will show you that the index contour right there says 1,400 feet. And the creek ends up being right there. So there's 1, 2, 3 contour lines between my index contour and my creek. So if my index contour was 1,400, this next contour line would be 1,390. That one would be 1,380. And the last one before the creek would be 1,370. So I'm going to go ahead and use that number, 1,370, as my final vertical height. And the vertical drop then would be 1,457 minus 1,370, which is 87 feet. Now we'll look at the video that shows me using the planimeter to find the horizontal distance that I traveled from this point to that point. So now you can see that I'm following along with the planimeter over this creek. I started from the 1,457 foot elevation point and I'm ending at the 1,370 foot elevation point. My horizontal distance is 0.922 miles. So what we just found was that the horizontal distance of the creek from this point to this point was 0.922 miles. So I'm going to go ahead and plug that in up here. And you should still have V, I erased mine, but V was equal to 87 feet. So go ahead and solve for the gradient. For part C, this is kind of an easier question. If you remember on the slide that I talked about gradients, I talked about competence as well. Competence is a word that, when we're talking about streams, means the size of particle that the stream can carry. So if you remember that gradient is equal to the slope or the steepness, that really does help. So if you have a higher gradient or a steeper slope, do you think the stream can carry larger particles or smaller particles? So let's look at the last problem, number 4. For number 4, we're going to be looking at 2 photographs of far northern Oklahoma City. You'll see that the first photo was taken in 1991 and was a lot less developed than the second photo taken in 2016. The next part of the problem says that we'll be studying the northeastern quarter of that area. Don't worry about finding the northeastern quarter of the area. I took a picture of only the northeastern quarter. Part A says to use a grid overlay to determine the acres of each land use type for 1991 and 2016. It also states that each grid cell is 0.1 miles and that there are 6.4 acres for each grid cell. So I'm going to go ahead and write that over table 8.4 because that'll be helpful. There's 6.4 acres per grid. Okay. So I'm going to be looking at these grid cells that you can kind of see to the right here. What I want us to figure out is how many grid cells can be assigned to each category of land use type. So I'm going to pause right there and let you see the picture. So in this picture, I'm going to show you a couple of them. I'll probably do the first two land use types. What you really want to make sure you do is assign all of the grids to some category. So there's 25 total grids. You want to make sure that in the end, all of your categories add up to 25 total grids. The first category is downtown and business. I'd probably say that the only downtown and business is like this guy and this guy right there. Those are probably like churches or something, but I would consider that downtown and business because of the parking lots. And I'd say that probably takes up like half of a grid cell. So I'm going to scroll back over here. And for downtown and business, I'm going to say 0.5 grids. Now, I could leave it at that, except I know that the answer needs to be in acres because that's what it says down here. So I'm going to go ahead and convert this using our conversion. The conversion we were given was 6.4 acres per grid. So if I multiply 0.5 grid by 6.4 acres per grid, I had to shorthand it because I'm running out of room, then grid cancels and we're left with acres as our unit. 0.5 times 6.4 is 3.2 acres. So I would say 3.2 acres is downtown and business. And I'm kind of going to keep a running tally of how many grids I have left. So I've used 0.5 grids. So I still have 24.5 left. So the next land use type is single family homes. Single family homes means houses that are lived in by one family. Rather than like an apartment complex that would be a multifamily house. So all of this development that we can see on the right side of the image here, those look like single family homes. Maybe some of these other guys sprinkled throughout here are single family homes. So I would say that looks like 2.5 grid cells, right? So that's like almost one. That definitely is one. And that's close to half. So all of those added up, I would say are 2.5 grids. So 2.5 grids. Again, I want to convert this to acres, so I'm multiplying by 6.4 acres per grid. 2.5 times 6.4 is 16 acres. So I would say we have 16 acres of single-family homes. So let me just go ahead and put the tally up now. I just subtracted 2.5 grids, so we're left with 22 grids. So go ahead and do the rest of them. Figure out what you think each thing is. I'll go ahead and say this land over here that has all of the lines on it, I would say that looks more like crops. Right, and maybe even this looks like crops because it looks like there's some lines in it. And I'm saying that because it looks like it's been harvested. But really, it's up to you what you think the land use is. Also, forest. You don't have to include this, but you see all of this like forested area right here. It's not much forest, but there are trees, and that's what it means by forest. So you can add up all of those to see how many forests there are. But make sure that all of your grids add up to 25 and all of your acres add up to 160, and do that for 1991 and for 2016. After part A is done, we can move on to part B. Part B is actually pretty simple. You just have to use an equation that we saw in one of the slides. Part B says, suppose there's rainfall of 3 inches over a day, and the soil was dry enough to accept infiltration. Using Table 8.4 and Table 8.5, calculate the total runoff from this quarter section in 1991 and 2016 in acre feet. So I'm going to stop right there because the next sentence does not apply. So I'm just marking through that sentence, and I'm going to go ahead and write down my runoff equation. So if you remember runoff, let me zoom in on that. Runoff is equal to the acreage times the runoff coefficient times the rainfall. And that rainfall needs to be in feet. So the acres we're going to get from Table 8.4. The runoff coefficient, we're going to use that table that was in the lab manual, Table 8.1. Right, these are our runoff coefficients. And the rainfall was given to us, but it needs to be in feet. So they gave us 3 inches of rainfall. 3 inches, we can see how many feet that is by dividing by 12 inches per foot. 3 divided by 12 is 0.25, 1/4, so 0.25 feet. So let me do an example. So for my downtown and business, first I'm going to multiply by my acres, which was 3.2 acres, and I got that from looking at Table 8.4. So 3.2 acres times the runoff coefficient for downtown and business, which is in this table. Downtown and business is 0.8. Remember that runoff coefficient is unitless. And lastly, times the rainfall in feet, which was given to us as 0.25 feet. So times 0.25. And I'm going to put feet right there as well. So clearly I ran out of room, but that is equal to 0.64 acre feet. And I'm going to do the same thing for single family homes. We have 16 acres. Single family homes has a runoff coefficient of 0.4. And I'm going to multiply that times 0.25 feet as well. And the answer to that is 1.6 acre feet. Okay, so go ahead and continue all of these and do the same for 2016 for each of the land use types. And at the end, make sure that you add up all of the runoffs for 1991 and add up all of the runoff for 2016. So then you can answer part C. I would look at which one has a higher total. So which year has more runoff? Why do you think that is? After you finish explaining the answer in part C, you'll be done with the lab. If you have any questions, just send us an email. Please hold on to your lab assignments until you come to class for Lab 9. And make sure that you don't go to lab the week of the field trip.